Okay, so welcome to this sixth lecture on model selection. And this lecture will be devoted to statistical learning. And the last lecture, the seventh one, will be also devoted to statistical learning. Today, we shall look at Vapnik's approach for statistical learning. And during the last lecture, we shall look at what happens when we look at the notion of convexification of the risk. So today we shall look at mainly binary classification. We shall be obsessed by binary classification, and we shall look at the hard loss and study the hard loss as Vapnik did it a long time ago now. And we shall look at two different approaches to do that: the global approach that was already used by Vapnik, and the refined one, which will be more based on the local analysis of the empirical process. So this is what we shall do today. And during the last lecture, we shall look at convex risks instead of hard loss. So first, I want to present you the basics. So our purpose is to use concentration inequalities to a better understanding of Vapnik's classical statistical learning theory. And we shall also use concentration inequalities to go beyond Vapnik's analysis. So the framework that we shall look at is looking at bounded empirical risk minimization for data which are IID. So this means that one observes IID variables, which are copies of variables xi, and which takes their values in some abstract space. And we look at some loss, capital L, and we shall assume that this loss is between 0 and 1. So 0 and 1 is not magic. You can put other constants, but the fact that the loss is bounded is important to use the concentration inequalities machinery. So retain from this that the loss is bounded. And our purpose is to estimate the minimizer of this loss of the expectation of this loss, with respect to the distribution of psi, which is of course unknown. So the two main examples that you have in mind are bounded regression and binary classification. So for bounded regression, what you look at is independent copies of a variable x, y. X is the explanatory variable, and y is the response variable that we shall assume to be between 0 and 1. So what you want to estimate here is the regression function, which is merely defined as the conditional expectation of y given x. But this is interpretable, of course, as the minimizer of the expectation of the least square criterion, the least square loss, over the L2 space. The binary classification is close in spirit to the preceding one, except that the response variable y is a label, that is, it belongs to the set 0 or 1. And the function of interest that we want to estimate is this time the Bayes classifier, which means that instead of minimizing the quadratic loss over the L2 space, we minimize it over the class of functions which takes the values 0 or 1. And this modifies completely the solution. The solution is this time the indicator function of eta being larger than 1/2, and eta is nothing else than the regression function in this case, and which is equal to, excuse me, there is a mistake, oops. Here it's equal to 1, given x is equal to small x. So it's the probability that y is equal to 1 given x, and this is the majority vote. You vote for 1 if the probability that y is equal to 1 is larger than the probability that y is equal to 0. And what we want to do is to provide a general analysis of the performance of the empirical risk minimization procedure. So what is the empirical risk minimization procedure? We already know what it is, but I remind you what it is. You look at the empirical criterion which is linked to the loss function L. So it's simply the empirical mean here. And you look at some model in the general space calligraphic S, and this model is merely a subset of calligraphic S, and the empirical risk minimizer over S is designed by taking the minimum of the empirical risk over capital S, if it exists, of course. So we want to analyze the statistical performance of f hat, this empirical risk minimizer, as an estimator of f, and we look as a loss, and we take as a loss function, excuse me, what is called the excess loss, and this is the natural loss function linked to the criterion, and this is merely the difference between the expectation of the loss under J, at point J, excuse me, and the expectation of the loss at its minimum. So if we come back to our main examples of bounded regression in the one hand and binary classification in the other hand, this leads to quite different solutions for the natural loss. The loss function in the regression case, we have seen that it is equal to the quadratic distance between f and j under the distribution of the explanatory variable x, while in the classification case, the loss function is also some kind of quadratic risk, because here you can take the square if you prefer. Because the function f and j take their values in 0, 1. So taking the absolute value or the absolute value squared, it's the same. But you have, as a novelty, you have this weight here, which depends, of course, of the difficulty of the classification problem. If eta is close to 1/2, you see that this loss is much smaller than if eta is away from 1/2. So if eta is away from 1/2, this loss looks like a usual quadratic loss, but if it is not the case, then you have something which is different. We shall come back to that later. So now we have to make the connection between the issue of controlling the risk of the empirical risk minimizer and suprema of empirical processes. And at this stage, we have two quite different approaches, which are the global approach and the local approach. So I have to explain you what I mean by local and global. So basically, the idea is very simple. Here we shall assume that J, that the true, excuse me, so you take the model S, and of course, by definition, f hat is the minimizer of ln of J when J varies in the model S. And what we shall take here as an assumption is just to make our life simple, because if it is not the case here, we can introduce a bias, and essentially what I am talking to you remains true, just adding this bias. But nevertheless, let's assume that, just to make our life simple, assume that the true belongs to the model. And if it is the case, of course, this means that the value of the empirical risk at f hat is less than the value of the empirical risk at f, because this is the minimizer, and f belongs to the set on which you have optimized your criterion. And so now, if you introduce the recentered empirical risk, that is, you look at ln minus its expectation, you can just rewrite the loss function as the sum between the variation of the empirical risk and the variation of the recentered empirical risk. This is simple algebra. And when J is equal to f hat, since you do know that the difference between ln of f hat and ln of f has a sign, it is non-positive, then you conclude that the loss here is less than the variation between f and f hat of the recentered empirical loss. So this is just elementary algebra and just using the fact that ln of f hat is less than ln of f. So this means that you have a connection now between the loss and the recentered empirical process, ln bar. And you have this control, which is made by the variation between the centered empirical process between points f and f hat. So now the global approach, which is the one which is used in Vapnik's book from the last century, this is the approach which consists of bounding the loss between f and f hat by the sup of ln of f minus ln of j. This is the global approach. But you can also make something which is which goes beyond that, and this looks very similar to what we have done in the white noise framework. That is, instead of looking at the global supremum, you first renormalize the empirical process by some weight, and after that, you take the supremum. And this is, of course, quite different, because doing this, you can take into account that the fact that the closer f is to f hat, the closer the empirical process ln of f will be close to the empirical process ln of f hat. Okay? But in any case, we shall use concentration inequalities to ensure that essentially the control that we have to make have to be done on suprema on the expectation of suprema of empirical processes rather than on the whole process. So what will make our life easy with the concentration inequalities is that we shall dispense ourselves to study the process in its full generality in some sense, but you just reduce the behavior of the process to the behavior of the expectation of the soup. And so this motivates the introduction of specific tools to control expectation of suprema. And we first link the expectation of suprema of the empirical process to something which is easier to study, and which is the expectation of suprema of Rademacher processes. So this is the first step that I want to do with you. I want to show you that through a simple symmetrization trick, we can reduce the analysis to this case. So what is this symmetrization lemma? So we take capital T to be a finite set, and we look at some empirical process. We look at vectors which are IID and taking their values in R to the power capital T. And the symmetrization inequality tells you that the supremum of the sum of the xit recentered is less than 2 times the expectation of the sum of the soup of the sum of the epsilon I xit, where the epsilon are what you think, that is IID Rademacher variables, which are taken independent from the original variables x1, xn. So I want to show you how to prove this symmetrization lemma. As you will see, this is a simple proof. So we introduce x prime, which is a copy of x being the x1, xn. And this is a copy which is independent of x. So when I do that, I simply use the fact that the expectation of the soup is always larger than the soup of the expectation. And of course, this remains true with conditional expectations, if I wish. To state that the expectation of the soup of the sum of the xit minus x prime it is which is equal to the expectation of the soup of the excuse me, not this, expectation of the conditional expectation of the same quantity, but given x. And this conditional expectation, because of this principle here, is always larger than the soup of the sum of xit minus the expectation of x prime it, but since x and x prime have the same distribution, it's also the expectation of xit. So what you get at the end of the day is that the expectation of the soup of the sum of the xit, which are recentered, is less than the expectation of the soup of the symmetrized process, sum of the xit minus x prime it. And now, by symmetry, we may use the fact that the epsilon I xit minus x prime it vectors and the same but without the epsilon are the same. You will not change the distribution of these vectors by multiplying by random signs, which are independent of everything, of course. Epsilon being independent of x and x prime. So this means that you can, for free, put some epsilon I as a multiplier in the above formula. And now you are almost done, because you can now bound this by the expectation of the soup of the sum of epsilon I xit plus or minus or plus the expectation of the soup of the sum of minus epsilon I x prime it but of course these two quantities are the same. And you get 2 times the expectation of the soup of the sum of epsilon xit. And this is the end of the proof of the symmetrization lemma. So this is the first tool, which is quite easy. And now you can use the fact that the variables epsilon r are sub-Gaussian. So I skip this contraction lemma because I shall not use it today. And I go directly to the suprema of sub-Gaussian random variables. So I want to show you that there is some general inequality here, which does not depend at all on the potential independence between the yt here. You do not use at all independence in this proof. So you look at some collection of real-valued random variables, which are simply sub-Gaussian. And you conclude that the expectation of their soup is less than the square root of 2v times the log of the number of variables. So let's see how to prove that, and then use it for Rademacher variables. So let's see how to prove this inequality for suprema of sub-Gaussian variables. So I remind you the assumption. The assumption is that you have the log of the moment generating function of yt, which is less than lambda square v over 2. This is true for all t, and this is true for all non-negative lambda. So this is what we have in our pocket, and we want to upper bound the expectation of the soup of the yt. And here we make something which looks strange, but however we do that, we multiply by lambda, and we say that it is always less, using Jensen's inequality, this is less than the log of the expectation of exponential lambda soup of yt. And now we use the fact that the exponential is monotone to say that this is also less than the log of the expectation of the soup of the exponential of lambda yt. And again, we make something which at first glance looks very strange. We bound the soup by the sum. So you could say, well, we could do that at the very beginning, but you know the idea here is that when you pass from the exponential here, when you look at the soup of the exponential, because of the exponential effect, you will have a record effect. That is, this soup here will be achieved by the variable which are the largest variance. And the sum will be because of the exponential, the sum will be of the order of the soup instead of being of the order of the sum of, how I could say that? Because of the exponential effect, the sum is still of the order of the largest one. This is what I want to say. Okay, so nevertheless, you bound it by the sum. And now you see that the interest of bounding it by the sum is that you can compute the expectation of the sum as the sum of the expectation. So this is equal to the sum of the expectation. And now all these guys are under control, because by assumption, I know that all these moment generating functions are controlled by the Gaussian one. So this is less than the log of the number of terms in the summand times the same quantity, which is the exponential of lambda b squared over 2. That is log of t, cardinality of t, plus lambda square, excuse me. Did I write it? No, square, yes. Square v over 2. So at the end, this means that you have lambda here as a multiplier. So I have that the expectation of the soup is less than the log of the cardinality of t over lambda plus lambda v over 2. And this is true for all lambda, so I can take the infimum. And this is explicitly computable. This is equal to, oops, excuse me. I've made something stupid. Up. And this is equal to the square root of 2 log of the cardinality of t times v. And this is exactly what we wanted to prove. So let's come back to the presentation. We have this control on sub-Gaussian random variables. And now you can apply it to Rademacher variables, since we know by Hövding's lemma that for a single sum of ti epsilon I, this single sum is sub-Gaussian with a variance factor which is given by the sum of the ti square. And so the corollary of the preceding result is just that for the expectation of the soup of the ti epsilon I, so for a Rademacher process, you do know that the expectation of this Rademacher process is under control by the square root of 2v times the log of cardinality of t, where v is merely the maximal norm square of the vectors t1, tn. Okay? We can improve on this bound. We can even improve on it by taking into account possible geometric properties of t. And we can replace the cardinality of t by something which is more subtle and which is the covering number. So the covering number is what? It's the maximal number of x separated elements in capital T with respect to the Euclidean distance. So of course, this number is always less than the cardinality of the set itself, but it may be much smaller. And if you use the crude bound that the number n is less than the cardinality of t, the evaluation which is here up to the constant 12 is the same as before. That is, you get sigma, which is the square root of what we call v in the statement before, and you get the square root of the log cardinality of t. So this is exactly the same statement as before, apart from the fact that you get here a more subtle quantity than the cardinality, and which takes into account possibly the geometry of t. So this is what people call a chaining inequality, because it is proved through a chaining argument that I have to detail right now. So this chaining lemma, you could see it as a way of improving on the crude bound, which depends on the cardinality, by looking at this Coot bound at different scales. Instead of looking at it at the largest scale, you look at it at different scales by looking at some dyadic scheme. So let me just introduce you this dyadic scheme. So what we simply do is that given delta, we consider some delta net. Sorry. This is a delta net, capital T. And what is a delta net? It's simply a maximal set of points in capital T, which are delta separated. And we have already seen that when you look at the situation, when you look at a maximal set of delta separated points, then it's a way of building a net that is a set of points which will help you to cover T. In other words, for all T in capital T now, I know, because of the maximality property, I know that there exists some T delta in capital T delta such that the distance from T to T delta is less than delta. Otherwise, this would be a contradiction with the maximality of the set capital T delta. Okay, so now I look at some dyadic scheme. I look some sequence at some sequence delta J, which is 2 to the power minus J times sigma. And I am defining some projection in the metric sense, pi J, which goes from T to T delta J, and which amounts to assign to T some point pi J of T, which is at distance at most delta J from T. The same as before, but now applied to delta J. And the trick now is to look at the Radmacher process, Zt equal to the sum of Ti epsilon I. And decompose this Radmacher process linearly in the following way. You look at Z of pi 0 of T plus the sum of the series Z of pi J of T minus Z of pi J of T. So don't be intimidated by the fact that I have written a series here, because since the set capital T is finite, at some stage, the pi n is identity when n is large enough. Because since the set capital T is finite, when n is large enough, since the points are separated by some quantity, if you are below this quantity, you cannot do anything else than attributing to T the value T. So at this stage, you have the identity, and then you have identity minus identity, and it makes zero. So this series is finite. It's a finite sum. and Siri is calling to me, is talking to me. Okay, so this is one point. The other point is that by definition, we shall choose pi 0 of t equal to 0 by convention. I decide this, and this not it has still the right properties because since we know from the starting point that the norm of t is less than sigma for all t in capital T, this means that the distance from t to pi 0 of t is also less than sigma, which is delta 0. So it's still the same definition as before. Okay, so now the soup of zt, I just have to bound it now by the sum of the soup of z. Now I use the fact that it is linear, pi j plus 1 of t minus pi j of t. And now I use the fact that the cardinality of the set of vectors pi j plus 1 of t minus pi j of t, this cardinality is less than the product of n delta j plus 1 by n delta j. It's controlled by the product of the cardinality of t delta j by t delta j plus 1. And which is less than the, by monotonicity, it is less than the n of delta j plus 1 square. This is in the one hand. On the other hand, when I look at the difference between the L2 norm of pi j plus 1 and pi j, this is less, of course, by the triangle inequality than the distance from t to pi j plus the distance from t to pi j plus 1. So this is less than delta j plus 1, which is equal to 3 times delta j plus 1. So now we are in a position where we can apply the lemma for sub-Gaussian variables. And if we apply it, we get that the expectation of the soup over capital T of z pi j plus 1 of t minus, oops, pi j of t is less than what? It is less than the square root of 2 times excuse me. Yes, square root of 2 times the again 2, the log of the cardinality, the log of the covering number delta j plus 1 t, and times 3 delta j plus 1. So this is the maximal square root of the L2 distance between of the vectors. The square root of 2 here comes from the statement of the lemma, and here it's the maximal log cardinality. Okay, so at the end of the day, what you get is something like 6 delta j plus 1 square root of the log of the covering number at the scale delta j plus 1. So now it's almost done. We collect these bounds here and we sum these bounds. And we get as an upper bound for the expectation of the soup 6 times the sum between 0 and infinity of 2 to the power minus j minus 1 sigma and log, square root of the log of n sigma 2 minus j minus 1 t. And of course, if you use monotonicity again, you can bound this series by the corresponding integral, square root of log x t dx. And this is the end of the proof. So it's not that complicated. It's a dyadic scheme, and you use the crude bound, but along the dyadic scheme. And at the end of the day, this improves on the crude bound. Okay. So now we are able to revisit Vapnik's theory. So we look at the binary classification framework, and in this case, the models are made of indicator functions. So the models can be identified as classes of functions, classes of sets, of course. Excuse me. So you have indicator functions on some class of sets. So the model can be identified with a class of subsets. This is what I wanted to say. So of course, this is not at all smooth models, and this means that you cannot apply at all usual statistical theory. Parametric models are prohibited here because of the lack of smoothness, and you cannot use the fact that possibly you have a finite number of parameters and use smoothness because you do not have smoothness. So for this reason, you use another quantity which has been introduced by Vapnik and Chavrankis, and which is known under the name of VC dimension, and which will play the role of number of parameters. So I give you the definition of the VC dimension. So the definition is quite simple. You look at the number, you consider some set with some finite set with cardinality equal to n, and you look at the collection of traces of the class of sets calligraphic A on B, on this set. And you look at the maximal cardinality of this collection of traces when you vary the subset, but keeping its cardinality equal to n. So you call this quantity M of n. Of course, M of n is always less than the number of subsets of B, that is, it's always less than 2 to the power n. But you can imagine situations where up to some point, up to some cardinality, excuse me, this M of n will be smaller than 2 to the power n. And if it is the case, you have by definition a VC class, and its dimension is defined as the sup of the n, such that M of n is equal to 2 to the power n. So if this quantity is finite, if it happens that at some stage you are no longer shattering all subsets of cardinality n, then you have a VC class and its dimension is given by this definition. And so what we shall see in a moment is that remarkably, when this quantity M of n is no longer equal to 2 to the power n, then it behaves like a polynomial with respect to n, and a polynomial which is very precise, a polynomial with a degree which is equal to the VC dimension. And this is the consequence of a subtle combinatorial lemma, which is due to Zauer, and which tells you that M of n is less than the sum of the binomial coefficients from 0 to d. So of course, if n is equal to d, this quantity is equal to 2 to the power n. But when n is strictly greater than d, this sum here can be much smaller than 2 to the power n. So first of all, examples of VC classes. So it's easy to see that when you look at half lines here, the VC dimension of half lines is equal to 1, just because when you look at a 2-point set, you cannot shatter this 2-point set by half lines. Think about it when you look at 2 points here. I can take this point without this one, but it's impossible to take this one without this one. Okay, I just have, so I cannot here create the single point, this one. So this means that you cannot shatter completely a 2-point set. And of course, this means that the VC dimension of the half lines is equal to 1. So this is a theorem which is more involved to prove that the collection of half linear spaces of Rd is also a VC class with dimension d plus 1. If you think about it, if you parameterize the borders of the collection of half linear spaces, these borders have d plus 1 parameter. So this is exactly the spirit of the VC dimension. It's a good proxy for the number of parameters. And this is also true that for Euclidean balls, it's a VC class with a dimension which is equal to d plus 1. And again, this is the number of parameters that you need to define a Euclidean ball. So I just want to say that this property of polynomial behavior can be obtained through an exercise that was given in the list of exercises of the exam. That is, m of n is less than ne over d to the power d. And so, as you see, this upper bound here behaves like a polynomial with degree d with respect to n. And the other thing that I want to say about VC classes is that you may prove for a VC class, this is a result due to Heusler, I shall not prove it, but this is true, that the covering number of a VC class with respect to any LQ distance, where Q is any probability distribution, this covering number is always under control, and it is controlled by, it is controlled by 1 over delta to the power d, okay, with a constant which is explicit as a function of d. It's a numerical constant c times d to the power d. So this is a property that we shall use afterwards. So maybe I prove Zauer's lemma, and then we shall make a coffee break. So the proof of Zauer's lemma, which is quite funny to make. It's a subtle but easy proof, but subtle. Zauer's lemma. So the proof is made by induction. On n. Building on the fact that when n is less than d, then the inequality is true. It's trivial. So we assume that for all VC class with dimension d, the property, the inequality is true. At range n minus 1. And we want to prove it at range n. So we take some set B with cardinality n, and we fix some point x null in B. And now we analyze the traces of A on B and on B minus this point. So we look at, if we look at the traces of A on B minus this point, they can be put in two categories. We have the complete traces, which are those for which the complete traces C, which are those for which both C and C union of the point X null belong to the traces of A on B. So this is what we call complete traces, and we have the others. So this means if we make a picture, we have this B here. We have this point X null that we have put here. And now we are looking at traces of the collection A on this set. Oops. So here's one, here's another one, okay? So when we look at a trace of A on the set B minus X null, you see that you have three situations in some sense. You have the situation where both C and the C union of X null is a trace of calligraphic A on B, and you have the situation where the parent X null is in the father, or the situation where X null is not. So there are three situations in some sense, but we resume it in either complete or others being one or the other. But we do not care of the fact that it is this or this which happens. Okay, so now that we have looked at these different ways of looking at traces, then we introduce the collection C of complete traces and the collection P of incomplete traces. And now, if you have well understood what happens, this means that when I look at the trace of A on B, they are made of the trace which are incomplete and 2 times the clarity of the trace which are complete. Because when the traces are complete on the B minus X null, this means that I have 2 traces when I look at the traces of calligraphic A on B. And now, if I look at the traces of A on B minus X null, this is exactly a partition. So you have the cardinality of P plus the cardinality of C. And now the trick of the proof, the trick is that C is a VC class with dimension less than D minus 1. Just because of the fact that the traces are complete. So if you imagine that some set is shattered, then the set to which I add the points x null will be shattered by A. So this means that the dimension is less than the dimension of A minus 1 because of this property. And this is the trick, because now when you look at the cardinality of B minus x null, if you look at the cardinality of the trace of calligraphic A on B minus x null, it will be less than the number m of A sub A computed at n minus 1. So this is less than the sum of n minus 1 k less than D. This is by induction. While now for C, because the dimension of C is less than D minus 1, this time you have the cardinality of C, which is less than MC n minus 1. And again, by induction, this is less than the sum of n minus 1k, but with k, which is less than D minus 1. And of course, this is also equal to the sum between 1 and D of n minus 1, k minus 1. And now you may use the Pascal's triangle, which tells you that n minus 1k plus n minus 1k minus 1 equals nk, to conclude that the sum of these two quantities here, the cardinality of C plus the cardinality of excuse me, I'm a bit lost. C'est ça. Excuse me. Cardinality of C plus B minus x null, cardinality of the trace of A on B minus x null will be less than what we were looking at, that is the sum of the nk from 0 to D. And this is precisely equal to what we wanted to control, that is the cardinality of B intersected with A. So this is the end of the proof of Laurent's lemma. Okay, so now we are in a position to finish the global analysis of the statistical performance of FAT, but this is what we shall do after the coffee break. So now we take a coffee break, and I'm back in 10 minutes. Okay, so see you in 10 minutes. Okay, so now we are in a position where we can finish the global analysis of the statistical performance of the empirical risk minimizer in the binary classification framework. So we start from the basic inequality, which tells you that the excess loss between F and F hat is controlled by the variation of the empirical process between F and F hat, and U bound this by the soup globally. This is a global analysis. So now there are some measurability issues. In order to avoid the measurability issues, we shall assume the collection to be countable. Otherwise, you have to take a separability assumption. But I don't want to stress on that. It's not the main point. From a constructive point of view, countability is enough because you can always assume that you have to compute minimizer up to some error, and so you can always assume in some sense that you deal with a countable subclass of the hook class. But I once again, I don't want to insist on that. So let's assume the collection to be countable. It's enough. You have the loss which is between 0 and 1, and so you can use Magdalenic inequality to ensure that your supremum here of the empirical process, this supremum, remains under control. And so you control, by the inequality above, you control the excess loss by some quantity E bold plus some error, which is the square root of 2x over n, apart from a set of probability less than exponential of minus x. So this is Magdalenic inequality, and the quantity E bold is nothing else than the expectation of the soup of the variation of the empirical process. So in particular, if you integrate this probability bound, this means that this E bold reflects really the risk under various powers that you can imagine on the excess loss, up to some corrective term, which is of order n to the power minus 1/2. But as you will see, at this scale, in this global analysis, we shall stick to orders of magnitude which are which are worse than n to the power minus 1/2. So it's not a problem. So to bound now this E bold, you can use the symmetrization lemma and say that this E bold is less than 2 over n expectation of the soup of an empirical process. And now we have several options. One option is to use directly the fact that the class here, the class of vectors which appear here has a cardinality which is under control. So if you use that directly, you use the cardinality of the log of of the vectors which appear, that is the vectors j of x1, j of xn. So of course, this is a random quantity, but it's a random quantity that we know to be under control anyway by a deterministic quantity through Zauer's lemma. So this is what we shall do as an option. But again, right now, what we can do is to work conditionally to the data first. You work conditionally to x1, xy, and conditionally to x1, xi. If we use directly the control that we have made of suprema of Rademacher process, then what we get is that the expectation of the soup is less than the expectation of the square root of 2 times the log cardinality, so this h of s that we have introduced here, times n. And now you can use Jensen's inequality to put the expectation under the square root here. And at the end of the day, you may always bound, as I suggested before, this expectation of h of s by the log of m of n, and use Zauer's lemma to get at the end of the day that the E bold is less than a quantity which is essentially up to constant the square root of the VC dimension over n times some slowly varying function, which is the square root of the log of n over d. So this is what you get by combining the above evaluation and Zauer's lemma. But you can also improve on this bound slightly by removing the log, just by using Euler upper bound for the metric entropy of S, and combine it with the chaining lemma that we have proved. And in this case, if you combine these two results, this allows us to remove the log. So the conclusion here is that using this refinement of the direct approach, which makes appear a log, you can remove this log. And what people asked themselves was that this quantity here, which has a strange shape, it is the square root of d over n, is it optimal or not? And the answer is yes, in the minimax sense. This is a result due to De Vrooy, Lugosi, and Lugosi. They proved that this order of magnitude here is minimax, but we have to understand and to know that this minimax is taken under a huge set of probability distributions, because you allow any joint distribution between x and y. If you allow any distribution between x and y, then this lower bound is not improvable. This upper bound is not improvable, excuse me, because there is a lower bound which has the same order of magnitude. So it seems to be the end of the story, but as a matter of fact, if you look closely to the proof made by De Vrooy, Gurfi, and Lugosi, it's clear that the distribution which are worse, the joint distribution which are worse, are those for which the probability that y is equal to 1 given x is very close to 1/2. And now you have to think about the meaning of this quantity. This quantity is introduced because you have in mind that you are in a binary classification situation, and you have in mind that there is some errors on the labels that you have on your data. But of course, this is a way to introduce some variability in the problem, but you don't have in mind that the data are so worse that the labels are attributed at random with probability 1/2. If you are in this situation, the problem is hopeless in some sense. So, of course, you are here looking at the excess loss, but you are looking at the excess loss in a situation where the smallest loss is not small at all. So, in some sense, you try to optimize the rate of convergence with respect to some quantity, which is itself very crude. So it's not very interesting. The most interesting situation is when the probability that y is equal to 1 given x is not that close to 1/2. And from this perspective, the story is not over, because you can ask yourself if there is something to do and something to gain if this probability is away from 1/2. So let's look closer at this case with this point of view, and let's look at what happens concerning the behavior of the loss. So we shall introduce a new notion, in some sense, a new quantity, which is a quantity which allows to link the loss with the variance. That is, we have this loss function, this natural loss function, the excess loss, and the excess loss can be completely disconnected to the variance of the loss. And we do not want that. We want to relate the excess loss to the variance of the loss. And this is what will allow us to localize our analysis. So in the regression framework, the link between the variance of the loss and the excess loss is very natural, because when you look at the variance of the loss, you look at the L2 distance square between the loss, the quadratic loss at point J and point F. This is very easy to look at. You simply write the difference of the squares as you use the usual identity, that the difference between the squares is equal to the product between the sum and the difference. And then again, you put a square. And you write it in this way. You make the difference appear, and the sum makes this appear here. And you use the fact that you are in a world where f, j, and y are between 0 and 1, which means that this quantity here is always less than 1. And so at the end of the day, the L2 distance between the losses is under control by the L2 distance between f and j within a factor 2. So this means that in this case, you have a link between the variance and the loss, which is very natural. In some sense, they are of the same, the variance and the loss are exactly of the same order up to some constant which is equal to 2 or 4, because this is a square. In the binary classification case, it's much more involved, and this is the heart of the matter now, because in this case, still you may upper bound the difference in L2 between the loss at point J and point F. You can bound it by the L2 distance between F and J. But the L2 distance itself, remember, is not naturally connected to the loss. The loss makes appear this weight here, which involves the difficulty of the classification problem. And this is exactly the heart of the matter now. The way the loss and the upper bound of the variance here are linked depend on the way eta behaves with respect to 1/2. So you can use a simple manipulation just to convince yourself that everything is possible. If you look at the quantity which is sensitive to the fact that eta is away from 1/2 or not, you look at 1 over 2 eta minus 1. You assume that this quantity to the power p is integrable, and you use Hölder's inequality. And if you use Hölder's inequality, you simply see that the loss, I've been too quick, excuse me. Oh, sorry for that. Okay, so if you do that, you see here that this is the loss here. This is another way of writing the expectation of, oh no, excuse me. This is the expectation of f of x minus j of x. This is this quantity. Okay, so this is our d. This is d f and j square. And you see that this d square is comparable to the loss, but with a quantity which appears here, which depends on eta. And you see that the loss is at a power which is any power between 0 and 1, in fact. So at the end of the day, this means that in this case, the function w, which allows to link the loss to the distance between f and j, the L2 distance between f and j, this w can be any power function. So this shows you that in some sense, in the classification issue, the link between the variance of the loss and the loss itself, the excess loss itself, this link can be done through any function in some sense, W. So if you look at the simplest situation, that is a situation where eta is away from 1/2 within a constant which is called h here, then in this case, the function w can be taken as epsilon over the square root of h. So this is what we can see from the notion that you have introduced, that is this function w, which makes a link between the variance of the loss and the excess loss. And now what I want to show you is why is it interesting? It is interesting to look at this link between the variance and the loss in order to localize the analysis of the risk. So first, I am making some heuristics, and then I will state a theorem. So heuristics is like that. You start again from the inequality, which tells you that the excess loss between f and f hat is under control by the variation of the centered empirical process between f and f hat. But instead of bounding globally this by the soup, we look at closely what happens when f is close to f hat. And to do that, we look at the scale, which is given by the distance d between f and f hat. And remember that this distance d is controlling the distance d square, excuse me, is controlling the variance. Okay, so we look at this scale here given by the distance d, and then we analyze the way the variation of the empirical process is done in a small ball with respect to this distance d. And what we have in mind is that this quantity here will be under control by a function phi, which takes into account, of course, the size of S. It's exactly what we have done. This is the analog of what we have done in the Gaussian case. In the Gaussian case, we have looked at some modulus of continuity, which takes into account the size of the model. And this is the same idea here. And this is performed through a distance which makes the variance under control. So we hope that this quantity will be controllable here. And the heuristics that we make is that if this is the case, we may commute this control on the expectation of the soup by using concentration arguments. We can hope that this will commute in a control which will be of this form, that is, the variation of the empirical process is controlled by this function phi of the distance between f and f hat. And if this is the case, this will mean, since we have this control from the beginning, which was true, this would lead to an implicit inequality which links the loss, the excess loss, to itself through this inequality here. And by some maximum principle, we can hope that the loss itself will be under control by epsilon star square, which is the solution of the border equation, which is given by that. So this is what we can hope. And in fact, it becomes a theorem by introducing proper constants. So the statement of the theorem is now the following. We are in a very general situation. Just the only assumption that we make is that the loss is between 0 and 1. And after that, there is no assumption. You look at a link which is done through this function W, which is almost anything reasonable. I mean, that is a function W which is non-decreasing and which behaves like a modulus of continuity. That is, the ratio of W of x over x is non-increasing. And this is the same for the function phi. And you assume that there is a link between this D, which controls the variance again, and the loss through a function W, which is almost anything. You assume that the modulus of continuity of the empirical process is under control, at least for scales which are not too small. And then you get that the risk of the estimator, the empirical risk minimizer, for the loss function, which is the excess loss, this risk is bounded up to constant by epsilon star, where epsilon star is exactly what we have seen before, that is the solution of this equation. So before proving this theorem, or sketching the proof of the theorem more precisely, I would like to show you what is the consequence of the theorem for binary classification. And let us focus on the situation where the noise is of an easy form. That is, we assume that the difficulty of the classification problem is measured by this quantity h, and that 2 eta minus 1 is away from 0, from within this quantity, which is denoted by h. So in this case, we can apply the preceding theorem with w of epsilon equal to epsilon over square root of h. And in the VC case, we can use the chaining lemma again, but this time we use the chaining lemma in a subtle way. That is, we keep the variance. So it's still there is some work to produce in order to prove that phi sigma is of this order of magnitude, but I don't want to go into the details. Essentially, it is using the chaining lemma. And you see here that you make appear a quantity which is very analog to what we got for linear models with dimension d in the Gaussian case, apart from the fact that you have this log which appear. And this log which appear is still there when you look at the conclusion of the theorem. The epsilon star, which is the solution of the equation which is stated in the theorem, this epsilon star is no longer d over n within a constant, but you have also this log which appears. So the precise result that we get is that we see d over n appear. This is very satisfactory. You have the quantity h which appears there, and you have this slowly varying function. And what is very nice and very cool is that for the critical value h equal to square root of d over n, the two quantities which are there, this one and that one, they coincide. For this critical value, d over nh is exactly equal to square root of d over n. And of course, this log of nh squared over d disappears because the log of 1 is equal to 0. So the lesson that we learn here is that if you look at the situation where the function eta is away from 0 within a quantity h, if this quantity h is greater than the square root of d over n, then you improve on classical results of VC theory. And if it is not the case, then you are in the situation where the classical results are unimprobable. You are trapped by the global minimax, and you end up with the usual rate of VC theory, that is the square root of d over n. But nevertheless, you can have now a continuous view of the problem, because when h is between 0 and 1, h is equal to 0, of course, you are in the worst situation. H equal to 1, you are in the best situation, where you have when you make appear d over n times the log. But between these two extreme situations, you have a variety of situations where the parameter h here plays an important role, as you see. And the beauty of the result which is there is that it is possible to show that from a minimax perspective, these rates are unimprobable in their world. That is, in the world of joint distributions, which have the margin condition that the 2 eta minus 1 is larger than h. So in this world of joint distributions which are gentle enough, the rate which is there is unimprobable, included the log factor, at least in the situation of half spaces. For half spaces, it's possible to show that the result is absolutely unimprovable. So now, before ending the lecture of today, I want to show you a sketch of the proof of the theorem. So we shall not give the proof in full details because it will take too much time, but I just want to give you the main steps and hope that since we have done similar computation in the Gaussian case, you will be able to fill the gaps. So sketch, so the general theorem. Sketch of proof. So we start from the inequality, which tells us that the excess loss is controlled by the variation of the empirical process between F and F hat. So remember that ln bar is nothing else of J, is nothing else than 1 over n, the sum of Lj of psi I minus expectation. Just to make sure that we understand ourselves. And now to localize, we decide to divide the empirical process by some weight, which has the following form. It's x squared plus the excess loss between F and J. And x squared will be taken as a constant kappa that will be chosen at the very end of the proof, times y times epsilon star square. And y is a quantity that will control the tail of the probability bound that we shall prove. And we look at the supremum of this quantity over S. And of course, if we do that, the excess loss between F and F hat will be controlled by this V times the weight, times L F of F hat plus X squared. So we find again this strange fact that the loss is on the left and on the right hand side. So of course, it will give you something if V is strictly smaller than 1, otherwise you have nothing. So of course, now we look at the event V less than 1/2. And on this event, L of F and F hat is controlled by X squared. So that the probability that L F of F hat is larger than X squared is controlled by the probability that V is larger than 1/2. And the way we shall prove the tail bound that we want to prove, that the probability L of f hat greater than kappa y epsilon star square is less than exponential minus y if kappa is well chosen. And so here it reduces to show that the probability that V is larger than 1/2 is less than exponential minus y if kappa is well chosen. So we are now in the situation where we have to control this supremum of the empirical process. So let's have a look at this empirical process. This empirical process is just L bar minus L bar of J over X squared plus L F and J. And J belongs to S. This is our empirical process. If we want to control its supremum, we do know that Lagrange inequality will be of some help. We shall use a version of it which has been given by Olivier Bousquet. I shall come back to it later. But nevertheless, you know that to control this, it will be important to control the variance and to control the L infinity norm. So the variance of L of F minus L of J is controlled by definition by our distance, D. And by definition, again, it's controlled by W, which establishes the link between D and the excess loss. So this means that the variance of the weighted version now, where I divide by X squared plus L, the variance will be less than 1 over X squared times W squared of the square root of L and J, of F and J, over a quantity that I can decide to put as L sup of X squared. So what I have done here is to say that the square of this quantity here is always larger than X squared times the sup between this one and this one, which is of course true. And now I use, why do I use? Nothing. I use just my brain to say that it's less than 1 over X squared, the sup over epsilon of W of epsilon over epsilon sup X squared. It's just a way of saying that the square root of L between F and J is any epsilon. So you have to bound this for any epsilon. And now if you look carefully as what appears here, you see that if epsilon is less than X, then by monotonicity of W, W of epsilon is less than W of X. And if epsilon is larger than x, then this is the monotonicity of W of epsilon over epsilon, which allows you to control it by W of x over x. So in both cases, in any case, you end up with a control which is 1 over x to the power 4 times W of x squared. Because you either use epsilon here or x, depending on the fact that x is larger than epsilon or epsilon larger than x. But in any case, you end up with that. So you see that the variance is under control. And now about the L infinity norm, when you look at the L infinity norm, it will N and J. If you look at it with its weight, which is LFJ plus x squared, you use the fact that L is bounded. It is between 0 and 1. To say that it is less than 1 over x squared, because the weight is always larger than x squared. So you have 1 over x squared. And now we may apply Bousquet's version of Lagrange inequality. So I'll just show you what is Bousquet's version of Lagrange inequality. The proof of it is made in the notes that you have. It's a refinement of the kind of proof that you have made several times by using the entropy method. But it's a version which is convenient for the application that you have in mind here. So we look at Z, which is the supremum of over T of Pn of Ft minus the expectation of Ft. And you assume that the norm square of Ft is less than V, and you assume that the subnorm of Ft is less than B. Then in this case, the Z minus its expectation is less than the square root of 2V plus 4B expectation of Z y over n plus 2by over 3n, except on a set with probability exponential minus y.
Monsieur, j'ai un examen à passer cet après-midi, par conséquent, je dois... OK.
Au revoir et bonne chance.
Pour un examen de simulation de monnaie, c'est seulement exposé, c'est ça?
Oui, oui.
Exposé.
Oui.
OK.
Mais
un article est difficile à comprendre. Est-ce que c'est grave si c'est difficile à comprendre?
C'est normal. C'est pas grave, c'est normal. Un article, c'est toujours difficile à comprendre.
OK. C'est-à-dire que je vous le représente, c'est une chose importante. C'est-à-dire j'expose cet éclat au sujet de quoi résoudre quel problème, c'est ça?
C'est ça, Xonier. C'est ça.
OK. OK, merci. Au revoir. Merci.
Au revoir et bonne année. So here, what I want to say is that if you compare it with with Lagrange inequality, what's new? With respect to the version that we have proved together, you have best numerical constants, but we don't care in some sense. But the most important fact is that we have replaced the expectation of the soup of the Pn of t square minus, excuse me, is replaced by V plus 4b expectation of Z. And this is important because you see that now it's ready to use inequality, since in the version that we gave, we were still in a situation where we had to analyze this quantity, but here this quantity disappears and it is replaced by something, of course, slightly larger than the maximal variance, but larger within a quantity which involves the expectation of Z, which anyway appears in the bound. So it's a version which is very convenient for the applications. So this is the version that we use. So using this version now, what we get is that V is less than the expectation of V plus the square root of 2 times W of x to the power minus 2 plus 4 times the expectation of V times y over nx squared plus y over nx squared, except on a set with probability less than exponential of minus y. And now it remains to control the expectation of V. Which still is something which is not trivial, because there is still some work to do to get that, but not that much work, but still and here we use the fact, use the assumption. The assumption that we have is that square root of n times the expression of the soup less than epsilon square of L bar and of f minus L bar n of j is less than phi of W epsilon. Phi W of epsilon. This is the assumption. And now to commute this into control for V, we need to use a device. This peeling device amounts to partition the set S into crowns. That is, you switch L between something like 2 to the power j plus 1 x squared and 2 to the power j x. And you make the union of these quantities with the ball L of j less than x squared. What I say here is that when you look any j, you can say that it is somewhere in these crowns here, or it is in the ball. So if you do that, and you will work a little bit, it's possible to show that the expectation of V is less than 4 times phi of W of x over square root of x squared. So you commute this control in expectation on both control of the expectation of the soup of the reweight. And as soon as you have done that, then at this stage the proof is almost finished, because when you look at the expectation you may use the monotonicity of phi W phi of t over t W of t over t to show that the quantity which appears, expectation of V, is less than some constant C over the square root of kappa. So it's simply using the definition of X and the monotonicity arguments and the control that we got before for the expectation. So at the end of the day, finally, using this kind of arguments, what you get is that V will be less than C prime, which is not C because you have to add the variance and the L infinity part, but which all are under control within the same kind of quantities. So you have this C prime over square root of kappa. And of course, it's enough now to choose kappa equal to 4 times C prime square to get that V is less than 1/2 except on a set with probability controlled by exponential -1. And of course, this implies that the bound that we were looking for is okay. That is, we have this. And with x squared, which is kappa y epsilon star square. And we have a probability bound that we can integrate and get the announced result. So this achieves the sketch of proof, because I have not done the proof explicitly with all the details, but this is essentially the proof. So to conclude here, you see that this local analysis really brings something new for classification problems which are not disparate in some sense. If you have a disparate classification problem where the labels are completely decided at random with probability 1/2, then you have the worst classification problems ever, and you have nothing to say more than the usual rates of convergence. But if it is not the case, the local analysis really brings something new with respect to the usual and the classical Vepnik-Chevarenkis analysis. Okay, so I stop here. Next and last lecture will be devoted to the analysis of what people call convexification of the risk. In order to get some computable algorithms, it's necessary not to look at the hard loss in classification, but some losses which are convex. And we shall see how to do that next time, which will be the last lecture. So stay safe. I hope to see you next week, and I shall send you, as usual, all the material by email at the end of the day. Okay, have a nice weekend, and see you on next Friday.